All right, it is 2, so we will get started here. One thing I did want to mention before we jump right into the PowerPoints is that I uploaded some more files under Blackboard. So if you go to the in-class test 1 folder, you should now see the study guides, and I'll move them around so they're better ordered. But these study guides are just another way for you to test yourself and see if you know the material. They basically just go over the PowerPoints, and if you can fill out the study guides without having to refer back to the PowerPoints, again, this shows mastery of the concept, and you should have no problems on the test. Like that, if you go in the in-class test 1 folder, don't have it yet, but what will be there will be all the study guide answers along with the answers to the problem we do in class. So if you come across something in the study guide, can't find it, can't find the answer to it, it will be posted in test 1 with answers. These study guides aren't counted for any grades. They're merely for you as a study tool and to test yourself. All right, so with that, we'll go back to the PowerPoint. So we left off, once I get this booted up, we left off talking about energy, enthalpy, and entropy. And we went through delta H, delta S, and delta G. And we talked about how thermodynamics and kinetics are separate. And we have our equation here, the Gibbs free energy equation that relates G, H, and S. And the way it's set up, if you know the sign of H and S, you can determine whether G will be spontaneous or not. So if H is negative, S is positive, it will always be spontaneous. If H is positive and S is negative, it will never be spontaneous. In the other 2 cases, it depends on the temperature. Now, energy, enthalpy, and entropy are what we call state functions. And a state function is a function that only depends on the beginning and the end point. They are path independent. And what I mean by that is the example I always like to use is climbing a mountain, right? So let's say the top of the mountain's high energy, the bottom of the mountain is low energy, and there's 3 different people going up this mountain. Person 1 goes in a straight line up the mountain. Person 2 does switchbacks to the top. And person 3 rents a helicopter, and the helicopter drops them right at the top. And all 3 of these people, if you just look at their change in energy, have the exact same change in energy because they started at the same point and they ended at the same point. Doesn't matter, they took different ways to get there. All that matters is where they start from and where they end with, and that is what a state function means. So H, S, and G are all state functions. So just a couple questions here about entropy. Remember, entropy means chaos. So I should have a poll with this to gauge our understanding. So 2 simple questions here. What has greater entropy? Liquid water at 0.1 C or ice at 0? And in the following chemical reaction that I'm showing, are we increasing entropy, decreasing entropy, or does entropy stay the same? So take a couple seconds, think about that, and answer when you think you have an answer. We'll do this. I'll let you think for like 30 seconds. All righty. So from the answers, everybody got water has greater entropy, so that's great, right? Entropy is chaos. In ice, you're kind of stuck if you're a water molecule. You can vibrate, but you're stuck in place. You can't really move within the solid. While water, you have full 3D movement in the liquid. So the water molecules are much more chaotic than ice molecules. However, we had a 50-50 split on B. So let's talk about this. Although I talk about entropy as chaos, because that's the easiest way for me to think about it, another definition of entropy is the number of states possible, a number of different conformations that you can be in. So here we have on the left 2 gas particles, and on the right we have 1 gas particle. Now the simplest way to think about this is, how many positions can I put 2 gas particles in a room versus 1 gas particle? And I'm going to break that down for you even more simply. Let's say I have a box, and this box has 4 positions. And I ask you, with one ball, how many different ways can you put this 1 ball in this box? And that should be 4, right? You can put the ball right here, or you could put the ball right here, and right here. So there are 4 different conformations. I can put 1 ball in a box with 4 slots. Now let's look at that same idea, but now with 2 balls. So let's go with this maroon, and let's go with, sure, purple. So I can put the purple ball right here. And I'm going to say 2 balls can't be in the same chamber at the same time. Therefore, I could put the maroon ball here, here, or here. That's 3 conformations. Well, what if instead I put the purple ball somewhere else? I'll put the purple ball right here and put the maroon ball here, here, here. That's another 3 conformations. So doing that, moving the purple ball around 3, 6, 9, 12, you can see there's 12 conformations. So I have more ways that I can arrange my 2 balls, more ways I can arrange my system when you have 2 particles versus 1 particle. So here the entropy is decreasing, because if you're in a 3D room, I have more conformations with my 2 gas particles than I do with my 1 gas particle. So that's another definition of entropy. How many conformations can you make? Which PowerPoint? This is a PowerPoint from Friday, 122. All right, any questions about the idea of entropy, what it means, or how by looking at a chemical equation you can kind of gauge it? All right, if not, we will move on. More conformations means increase of entropy. The more the more ways I can arrange my energy, the more entropy it has. Another example is a deck of cards. The most ordered way you can have a deck of cards is, ace through king, and let's just say you do that for hearts, spade, diamonds, and clubs. So it's perfectly ordered. That's a state of 1. And then I throw up my deck of cards into the air. What are the chances they land in perfect ordered like I had them? 0, right? Because that's a very ordered state. So they have a million different possibilities they could be in. So when I let them loose, the universe wants to go towards entropy, wants to go towards these different conformations. So they will go out these different conformations. Entropy is chaos, means more ways I can distribute energy. All right. So here's a little review. We talked about a lot of these on Friday. Let's see if we remember what the answers are. There's some quick true and false for us as a way to review. Do you remember Monday or Friday? Or was that 3 days, beginning of the semester, already out of your head? I'll say give a minute for these true and false questions. Do about 10 more seconds. All right. So a spontaneous process always happens very quickly. That is false. Again, remember the iron rusting or a car rusting if you leave it by the beach. That'll take a couple of years for it to happen. It's spontaneous. It will happen. Or another process that's spontaneous is that the sun is going to explode one day. That is spontaneous. It's not going to happen for a couple more billion years, but it will happen. Okay. Number 2, a non-spontaneous reaction will proceed spontaneously in the reverse direction. That's actually true. That is true. So let's do a quick chemical reaction, or not a chemical reaction, but the idea of a chemical reaction. So I have a hill. And on that hill, I have a boulder at the bottom of the hill. So let's say I don't push on this boulder. Nothing's acting on the boulder. Is the boulder going up the hill a spontaneous process? What do people think? Is the boulder going up the hill a spontaneous process? Well, if we just leave it alone, will that boulder go up the hill? Nope. Yeah, pretty obvious, right? It's not spontaneous. Okay, that's one direction of the equation. My other direction of the equation is, well, if one direction is going up the hill, then the reverse process is the boulder going down the hill. So if I put the boulder at like top of hill, let's just assume it's not like on a completely flat place. Let's assume it's on like a peak. Eventually, that will go down the hill. Spontaneous. Another example, my pen dropping from my hand, hitting the table. Spontaneous. The reverse process, pen going back into my hand. non-spontaneous. So if you have an equation, a chemical equation that's reversible, if one way is non-spontaneous, by definition, the other way has to be spontaneous. They both can't be non-spontaneous or you don't have a reaction. All right. And lastly, a spontaneous process can occur with a large decrease in entropy. True, right? Go back to our equation, delta G equals delta H minus T delta S, right? So large decrease in entropy means delta S is negative. And remember, to be spontaneous, delta G has to be negative. That's fine as long as entropy is negative as well. That's the only way this will happen. An example being water freezing to ice, right? We said just on the last slide that liquid water has less entropy, or sorry, has more entropy than ice, right? So when you take liquid and you freeze it, entropy decreases a lot. But water freezing is spontaneous at certain temperatures, below 0 degrees centigrade or 273 Kelvin, right? Because when you freeze water, you release a lot of heat by doing that. And so the loss of entropy is made up for heat loss. And as long as you're below 273 Kelvin, the heat loss is more important than the entropy loss. If you're above the freezing point, the heat that is put into the universe is too small to battle that entropy loss. So thermodynamics, Gen Chem 2 all over again. Questions about those ideas? All right. So our last question for this PowerPoint, then we'll move on to Monday's PowerPoint. It's just some quick calculations. So I will do A for us, and I'll give you a minute to do B. So consider a reaction where delta H equals 15 kilojoules, delta S equals 50 joules per Kelvin. Is this reaction spontaneous at 10? All right. The equation we want is delta G equals delta H minus T delta S. Some things when it comes to biochemistry and actually math in general, always make sure your units match. So let's take a look at what I mean. So if I just plug in without paying attention to any of my units, I say delta H is 15 kilojoules minus T, and I'd say that's 10 centigrade multiplied by delta S, which is 50 joules per Kelvin. First off, we have a problem with temperatures. My S is in Kelvin, but my temperature is in Celsius. That won't work because the unit of energy is the joule or the kilojoule. It's really the same thing. So my final answer needs to be in energy. So temperature needs to cancel out. So what I'm going to do is I'm going to convert from Celsius to Kelvin. Hopefully you have this by now. But to convert from Celsius to Kelvin, you just add 273 to it. So that's 283 Kelvin. The other unit we have to look at is kilojoules in joules, because eventually we're going to subtract these two numbers. And when you add or subtract stuff, they have to be in the same units. Like, I can't say I have 5 marbles, subtract 2 pennies from those marbles. That makes no sense, right? That sentence makes no sense. When you add and subtract stuff, they have to be in the same units. You can multiply different units, but not add and subtract different units. So what I'm going to do is I'm going to take my 15 kilojoules and I'm going to convert it to joules. There are 1,000 joules and 1 kilojoule. So that's 15,000 joules. Now I can do my math. So delta G equals 15,000 joules minus 283 Kelvin multiplied by 50 joules per Kelvin. And hopefully I did my math right, because I have not checked this today. That I put this in right? Let's see what I got for this. Positive number of 850 joules. Non-spontaneous. And that is how you use the delta G equation with numbers. So I'll give people like 2 or so minutes, 2-3 minutes. Try and set up B, see if you can get an answer for that. So work on B. And if you have questions, let me know. Minus 2650 watts. No answer is complete without units. So delta G, joules. Yep, always remember that. When doing math, especially science, if you just put a number down, that number does not mean anything unless you have the units with it. So delta G, delta H minus T, delta S. So let's see, I'm gonna do the same thing, 15,000 joules minus, this will be 273 plus 80, which is 353 times 50 equals minus 2650 joules. Any number that is negative is a spontaneous reaction. Any questions about Gibbs free energy equation? All right. Oh, and by the way, you don't actually have to say no. If you don't have a question, I take silence as no answer. Yeah. So let me go to, or sorry, I take silence as no question rather. Go to today, more review, yay. Don't worry, we'll get on new stuff soon enough. But since this is a level 4000 class, I kind of have to make sure we remember the stuff we should have learned back when we were young. So if you remember all the way back in Gen Chem 1/2, not only is free energy described in terms of entropy and enthalpy, we can describe it in terms of concentration of reactants and products. And we express the concentration of reactants to products as an equilibrium constant or a constant of some sort. So if we're at equilibrium, the ratio of products to reactants is KQ. If we're not at equilibrium, then we call that ratio Q, or the reaction quotient. So it's called KEQ if at equilibrium, Q if it's not at equilibrium. So let's look at our very simple reaction. These smaller letters are numbers of moles. And the big letters are fake compounds. So A plus B makes C plus D. At KEQ, our equilibrium constant is the concentration of C raised to the power of how many moles of C we make. So we're raising each concentration to the power of moles from our chemical equation up here, right? So that's why it's C times D divided by A times B. And we can relate that to Gibbs free energy by saying Gibbs free energy equals delta G naught plus RT ln of KQ, natural log of KQ. This delta G naught, we call that standard free energy. What that means, it's free energy under certain conditions. And the reason why this is helpful for us is that chemical equations, like if we want to compare different chemical equations, they all happen under different conditions, different concentrations, different temperatures, different pHs. So it's really hard to look at delta G between these different equations and get anything meaningful out of it. However, if we say, okay, we're going to have all the reactants at 1 molar, we're going to have all the products at 1 molar, temperature is going to be a set number, pH is a set number. Then we can look at different equations and look at their free energy and compare different equations and say, okay, if the conditions are the same, equation 1 is more energetically favorable than condition 2. That's what standard free energy allows us to do. Biochemists have their own standard state, and it's called delta G naught prime. Yeah, weird name, I know, but that's what this symbol is. This is a naught and a UGHT. This is prime. So delta G naught prime. And we say biochemical standard conditions are 25 C, 1 atmosphere, pH of 7, all concentrations at 1 molar. So that's how in the body, we're going to say to compare different reactions, we're going to measure the free energy change under these conditions. Now going back to our delta G equation up here, if we're at equilibrium, then delta G is 0 based on the definition of delta G. Then we can solve for our standard state by saying delta G naught prime equals minus RT ln of KEQ. R is gas constant. T is temperature. This KEQ, again, is our equilibrium constant that is reaction dependent. Each reaction has its own value of KEQ. So there was about 2 to 3 weeks of Gen Chem 2 in about 5 minutes. So let's work with these equilibrium constants because we do use them quite a bit in biochemistry, especially when it comes to metabolism. So I have solved delta G naught for me with those conditions. I give you R and I give you T. Then B, get the equilibrium constant for that reaction, given delta G naught, given T, given R. So I'm going to give people a couple minutes to work through this. If you get an answer and you want to check it to me, feel free to whisper that to me and I can tell you, yeah, that's what I got, or no, that's not what I got. If you get stuck, you want help, again, feel free to send me a private message if you want, and I can help try and help work through that with you. Otherwise, let's do a little math here. See if we can figure out these math problems. And just as a reminder, all these questions should be in the in-class test 1 folder. This one's Jan 25th. And all the lecture material that we go over in these in live sessions will always be posted there. And the answer keys will be posted in the answer folder. So let's take a look at A here. So get my pen back out. Helps. Delta G naught equals minus RT ln KQ. So KQ equals concentration of C multiplied by the concentration of D divided by concentration of A multiplied by the concentration of B. Temperature, we need that in Kelvin. So T equals 273 plus 25 equals 298. Gas constant is a given. All right, so now let's put in the numbers. Minus 8.314 times 298 times the natural log of, so C is 3 times 5 divided by A is 10 times 15. And when you do that, I believe, let me just double check my calculation. You get a positive 5704 joules. Joules per mole. Which makes sense that it should be a positive number, because at equilibrium, the concentration of products is less than the concentration of reactants. So non-spontaneous. We don't want to make more products. In fact, we want to make more reactants at equilibrium. So questions what I did for A. All right, so let's move on to B then. Delta G equals minus RT ln KEQ. Delta G is minus 29 kilojoules per mole equals negative. Well, R, already a problem here. That's in joules. So I'm going to convert that to kilojoules, right? Remember that there are 1,000 joules for 1 kilojoule. Therefore, this number is 8.314 times 10 to the minus 3 joules per mole. Okay. Basically, just take your number divided by 1,000. Whoops, kilojoules to get into kilojoules. If you wanted to instead to change your delta G number into joules, that's fine too. You just take delta G and multiply by 1,000. Either way, get the same answer. Multiply by temperature in Kelvin, so 298, multiplied by ln KEQ. That's our first step. Then what we want to do is get ln KEQ alone. So just a little reminder about how algebra works. If you have a variable and you're trying to take the natural log of that variable, or if you're trying to take the log of that variable, you are not allowed to touch that variable until you've taken care of the natural log or log, right? So right now, this KEQ is more or less trapped by the ln. So I want to get that alone on its own side of the equation. So I'm going to divide each side by RT. And when you do that, you should get ln of KEQ equals 11.7, if that calculation's right. So the way I got that is that 11.7 is taking delta G naught and dividing it by negative RT. So hopefully I did that math right. Then to get rid of a natural log, you take each side and you take the exponent of it. So you should notice right on your calculator, if you have an ln button, the second function should be EX. Or if your calculator says EX, the second function should be ln. Those two processes, exponent and ln, are like opposite processes. It's like how multiplication and division cancel each other out. So if I try to take the natural log, or if I try to take the exponent of a natural log, they cancel each other out. And I'm left with KEQ equals the exponent of 11.7, and KEQ equals 121,177. KEQ 21. And something I would love for you to start training yourself, which is a very valuable skill, is I want you to start and ask yourself when you get an answer, does the answer make sense to you? Start thinking outside of, this is what my calculator says, so it must be right. Or this number is really big, so it must be wrong. We can start rationalizing this. Delta G was a negative number. Therefore, KEQ, or at equilibrium, we're going to favor products over reactants. Remember, a spontaneous process means delta G is negative. And if it's spontaneous at equilibrium, we will have more products than reactants. KEQ is the ratio of products divided by reactants at equilibrium. Therefore, if G is negative, KEQ should be greater than 1 because you have more products than reactants. Here, our KEQ number is greater than 1. So we can have a little confidence in our answer. It's still possible we did the math wrong, but at least KEQ is greater than 1. So that's a good sign. All right. Any questions about how I did this problem? All right. If not, we will move on then. All right. The next thing we're going to talk about are catalysts, more specifically enzymes. So chapter 7 or 8, I forget, like near the end of this semester is when we're really going to go into enzymes in depth, but we're going to begin and talk about the basic theory right now, because you should know about catalysts from organic chemistry. And what a catalyst does is that it speeds up the rate of a reaction. An enzyme is a catalyst inside your body, an organic catalyst. Like over 90% of the time, they're going to be enzyme or proteins rather. Not always the case. You have RNA enzymes as well, ribozymes. There are some DNA enzymes. They're super rare, but they do exist. So you can have, most of them are protein. If not protein, then probably RNA. And super rarely they can be DNA. And enzymes, for the most part, they only do one reaction, but they do it really well. Organic catalysts that you learned in organic chemistry, they will have side reactions. And if you get like 90% of your product as a yield, that's a really good reaction. Enzymes, they can do like 99% without any side reactions, no problem. They are super specific in what they do. And that makes sense because the cell is a very regulated process. And a cell probably would not live very long if its enzymes had like a 10% chance to fail any given reaction. That's just too much error for life. So if we look at the left-hand side here, this image, what we're showing is free energy versus reactant coordinates. So free energy going from positive G to negative G. Reaction coordinates basically means like the start of the reaction when you're only reactants and the end of the reaction when you're only products. All right. So we have two curves here. The blue curve is the uncatalyzed reaction. The red curve is the catalyzed reaction, right? So what an enzyme does is that it lowers the transition state. The transition state is basically you're half a reactant, half a product. You're transitioning from a reactant into a product. This is the most unfavorable state to be in. You don't want to be the transition state. So it's really hard to become the transition state. And the energy difference between a reactant and a transition state is called delta G double dagger. That's what this symbol is called. It's called a double dagger. What an enzyme does is that an enzyme lowers this activation barrier. All right, so I do have a question for all of you. And let me see here. Did I make a poll? I did not. All right, so I guess answer this yourself. You don't have to say it in chat or anything, but I want you to commit to an answer. So I want you to think about, how does delta G change between a catalyzed and uncatalyzed, not unanalyzed, uncatalyzed reaction. Keep in mind that the more negative a reaction, the more favorable it is, the more energetically favorable it is. So if I'm catalyzed and uncatalyzed, how does delta G change? So take about 30 seconds and commit to an answer. That's what I want from you right now. Commit to an answer. And once you commit to an answer, hopefully you have the logic of why. But if not, try to logic out why you came to that answer. All right, I'm going to try this little feature. So if you think delta G decreases in the participants tab, press the yes button. I've never tried this before. If you think delta G decreases, becomes more negative when you become a catalyzed reaction, press the yes button. And that should be like if you go to participants. If you think delta G increases, press the no button. If you think delta G doesn't change, I don't know, press the coffee cup button under the more and need a break. So do you think delta G becomes more negative? Yes button. Delta G becomes more positive? No button. Doesn't change. Coffee cup. Got one for yes, one for coffee cup. All right. So the answer is delta G doesn't change. Between a catalyzed and uncatalyzed reaction, delta G never changes. And that's an important part of a catalyst. A catalyst does not change the thermodynamics of a reaction, it just speeds up the reaction. Remember, thermodynamics, which is delta G, and kinetics, which is speed of reaction, are separate. So just because you speed something up does not mean you change the delta G. Delta G is the same. And that's because all a catalyst does is that it changes delta G double dagger. The height of delta G double dagger, that's the speed. The way I always think about it is like if you're running up a hill, it's much faster to run up the catalyzed hill because it's smaller than it is the uncatalyzed hill. So an enzyme, a catalyst, lowers that activation barrier, but the energy of the products in the reactants are the same. So at the end of the day, you're going to have the same amount of products. You're going to have the same amount of reactants. All a catalyst does is that it will get you there faster. All right. Any questions about our tour back into catalysts? If not, I think I will call it there because it's basically 2:50. So we'll pick up right after this slide on Wednesday. As always, I'll put a homework up on Wiley Plus. So remember, that's Tools Wiley. You will have a week to do it. So your first homework assignment is due this Friday. And then basically you're going to have a homework due every Monday, Wednesday, Friday. So make sure you're checking that. If you have any questions about anything, something pops up, let me know. Question about homework, whatever, just email me. Otherwise, that's all I have for you. And I will see people hopefully on Wednesday. Have a good day, everybody.